talking about earthquakes and seismic waves. I got a nice little picture here kind of showing what some of the aftermath can be, and we're just going to move right into it. So first of all, an earthquake is the vibration and shaking caused by movement at faults and plate boundaries. We're going to talk about what causes it, but you can see a picture right here. You've got a fault. Um, Plate boundaries are where there's a lot, the large crack in the earth where two plates, tectonic plates, are grinding and moving past each other. There's a lot of friction. It builds up, and eventually, sometimes that snaps. The plates slide, or the faults, they kind of, all the pressure builds up, and then they just kind of break free. And that shock wave sends energy through the earth, and that's what we call an earthquake. One thing I'm wondering if you guys can pick up, you see this picture I've got right here. See, there's like, earthquakes where the tension or pressure or whatever, all the friction and energy is released. But what kind of fault is this? Look at this picture. Tell me, obviously you guys are just watching the video, but what type of fault is this? You can see a fault right there. You can see some layers and see if you can figure it out. While I've been talking, I wonder if you've picked out that this is actually a normal fault. You can see that the hanging wall did go down, footwall relatively went up, but that would be a normal fault. A couple more terms. You don't need to write the words more terms, just these terms. One word is the focus. Focus is also sometimes called the hypocenter. This is the exact point along the fault where the earthquake happens, or where the pressure, tension, compression, whatever, all the energy is released from. That's the focus. It's inside the earth. It's along the fault or plate boundary, and the epicenter is the spot directly above that on the surface. So if you ever look at a map and you say, this is the exact epicenter of the earthquake, like that's directly on the map. The epicenter is basically just the surface right there, the surface above the focus. So they're connected. Know the difference between these two terms. I like to think of the focus as being where all of it was focused, and then it spread out from there, and the epicenter is just right above the focus. Seismic waves. Seismic waves are vibrations that carry the energy of an earthquake. They travel in waves, similar to sound waves, so they bounce off of things. If you guys have ever yelled into a wall, like sometimes when I'm in the classroom and I'm like, see, sound travels, it bounces off walls. Everybody knows it already, but I can put my face almost right up next to a wall and yell into it, and everybody hears what I'm saying. It sounds muffled, it's distorted because I'm not speaking directly at people, and you're hearing a vibration. The first thing you hear is actually vibration rather than my voice. But seismic waves work similarly. There's kind of this movement and kind of like shaking and pulsing. Sound waves move by moving air molecules, and seismic waves move by moving molecules of the earth. So rock, soil, water, those things. They travel differently through different materials. So I just listed off a couple, rock, soil, water. They travel differently through different things. And so much like you can imagine sound, if you take two rocks and you bang them together underwater while you're underwater, you can hear a knocking sound. And if you bang them together above the water, you can hear a different sound. And if your head's out of the water and the rocks are underwater and you hit them together, that could make one sound. And then if you do vice versa, it's kind of the same thing. But you get different sound waves traveling through different materials. And it's the exact same thing with seismic waves. Don't write all these lists. These are the ones we're going to go over. But please write types of seismic waves. That's going to be your heading, and you can see a little preview of our types of seismic waves we're going to get into. The first type are P waves. P waves are also called primary waves, or that's why they're called P waves. Let's get that little animation going. And you can see right here we've got this kind of like slinky looking thing. It's kind of just like, you can see it kind of ripples. Very satisfying. P waves compress or push and expand matter like a spring. They move the fastest, and that's why they're called primary waves. And these travel through solids and liquids. Let's see that animation one more time. So it's compressing. Some of these bricks are expanding, and then some are compressing or squeezing. You can kind of see them squeezing just like that. And you can see down here in this picture, there's like this, kind of, it's moving this way and then moving that way, like squeezing together. These are compressing together. But then you notice right here, these are moving apart. And so you can see the fence is all broken. The next type of seismic wave are S waves, or is S waves. S wave stands for secondary waves. They move matter side to side like a snake or up and down. And let's take a look at that animation. These show up after P waves. That's why they're called secondary waves. And they can only travel through solids. They don't travel through liquids. And the best way I can explain this is if you ever think about being inside of a pool, if you're in a pool and you're ever like trying to make a wave, like move your arm kind of slowly and make like a big wave, whether you've got like an inner tube or whatever, if you just push the water in front of you, like kind of like a wall, it's going to move. It's going to make a nice ripple, and the ripple's going to come out from where you pushed. So it's like, you push the water in front of you, kind of like, let's say you've got what do they call those little foam boards? You push the water out like that, and it moves the water in a nice ripple away from you. But if you try to do an S wave motion, like if you were to like wave your hand like a snake in front of you in the top of the water, it's not going to make a snake pattern. It's just going to make normal waves right in front of you. So basically, when you try to like do that snake pattern, like with your hand in the water, thinking you might get a sideways ripple, you're going to find out pretty quick that all that sideways motion is lost, and it's just going to go forward like a normal, basically like a P wave. And that's why. So like the reason is, and I wish we were in class so I could take my springs out, but you've got this kind of like whiplash, kind of side to side snaking motion, and that motion needs to have some kind of solid connection. So we could do it with a string, we could do it with a wire, we could do it with a slinky, we could do it with a long bar of metal or rock or wood. But like if you've got like a long pole. But it's not going to happen with something like a liquid, because those particles, the chemical bonds, are just going to kind of slide past each other and they're going to let go. And so S waves do not go through liquids, whether it's water or lava or something else. Again, let's take a look at that little animation. They kind of have this like, if you've ever like tried to, if you've ever had like an extension cord or a long hose in your yard and you did like that little whiplash thing to kind of make it move, it kind of moves just like that a little bit. Here's a picture of an earthquake, or some place that kind of had this earthquake happen right next to, what is this, train tracks. And so you can see those got kind of bent and rippled. And the last type of seismic wave, those are surface waves. Surface waves move the ground in all waves, combining in P and S waves on the surface. Slowest but most destructive, and the circular motion can move like crashing waves. And so I don't have a cool animation like this, but what I will say is, imagine you've got your P waves, compression and pushing and kind of push-pull, and then you've got this side-to-side or up and down. And really what happens is you've got this kind of like circular crashing. It's like it moves back and then moves forward, or it moves back, moves up, forward, and down. So it's like, if you've ever watched, I don't know if you've ever been in an earthquake, but it's basically like, a lot of people think, well, you could just like hold still so it's not shaking so bad, but it's erratic, and it's not predictable, and it's this weird kind of like forward motion. It's not a constant motion that goes the exact same way. Sometimes it's a big push, sometimes it's a little one, but it's this shaking, and it's very unstable. And you can see here there's just this, so this is really like if you've got that extension cord in your yard, or like a long string or something, and you just kind of like whiplash it, it's going to travel, all that energy travels down that wire or that string or that, extension cord. How do seismic waves travel through the earth? Well, there's a layer. Earth has layers, and some layers are liquid and some layers are solid. And so right here you can see, right here is where the earthquake happened, the focus, right there in the crust on this side. And it sends these seismic waves out. And, I'm not going to describe what's in this picture exactly. I mean, you guys can read it. We've got our key right there and some descriptions. But when some people say, how could you really know what this stuff is, Mr. Reed? How could anybody really know what these layers are made of? And so this is one of those bits of evidence that kind of adds to the pile. Earthquake scales. So we got a little picture here. There's our P wave, S wave, and this R means Rayleigh or Rayleigh waves. Those are a type of surface wave. And you can see it's like a bump, and then boom, 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 boom. I hope you like my sound effects. Measuring earthquakes. Once again, we're going to keep this one short, but don't write that stuff down. Just write measuring earthquakes, and you can pause right now if you need to write that down, but I'm just going to move on. The scale we use. I'm not going to go a ton into all the other ones, but the scale we currently use. When you hear the magnitude, 8 magnitude earthquake, we're talking about moment magnitude scale. And this is a mathematical equation. It's a measure of the total amount of energy released during an earthquake. This is the scale that scientists use. You ever hear about the Richter scale? When I was a kid, we did. We don't use the Richter scale anymore. The Richter scale, we'll get to that in a second, but it's not used. We use this moment magnitude scale. And so down here you can see a 5.8. That's what a 5.8 looks like as far as like if we compare this sphere to a, amount of energy released. This is a 7, just 1.2 up, and this is a 2 up from that 7 to 9. Huge. And remember, these are spheres. You can see like a three-dimensional image. These are spheres, so they're three-dimensional. It's not just a circle, which means they're way huger. So the amount of energy released from a 7 to a 9 is insane. 5 to 8, 5.8 to 7 is big. 7 to 9 is immense. And so when you go from a 7 to an 8, it's pretty big. When you go from an 8 to a 9, it's even bigger. It's like exponential growth. And so when we talk about like, when you don't see that many 9s, there's like a total of, I don't know, 8 or something in the last recorded history. That's because they're rare. It's rare that that much energy builds up for that long and then releases in an earthquake. Now, they've happened throughout history before we were recording, but it's pretty rare. It's, what do they get? Like one per decade, maybe. Maybe once every other decade, but they're big. And so we got some in Japan, we get them in, Indonesia, but they're big earthquakes and they're massively destructive. Don't write any of this. You can write it, but you don't need to. I'm not going to test you on this. The Richter scale is an old scale we used to use, and it measures things by vibration. So you can see kind of like the size of vibrations down here. It's like, recording on this drum of paper. And the Mercalli scale. This was really, really useful. You can see the date down here in this picture, 1935, magnitude 6.2. Back before we had these kind of, back before we had these recording devices and this worldwide system of seismometers, we had to use eyewitness testimony or whatever. And so they would check in with people. What did it feel like? My windows were shaking, or some things fell on the floor. The chandelier was swinging back and forth. The ground cracked open. My foundation had a crack in it. My drywall had a crack, or whatever. So the closer you are to the center, the more devastating it's going to be, and the further you go out, the less. And so they would say, okay, well, I just had like a little like rumbling, or it sounded like a truck drove by, or over here might be something a little bit more intense, and then over here it's like, okay, yeah, I've got a crack in my foundation and a window broke. So again, we don't use this anymore because we have science and we have scientific instruments and we have things, we can passively monitor these things constantly and have them sent to computers. We don't need to knock on people's doors and have them report what they felt. The last thing I just want to go into, and now we're done with the kind of basic notes, but one big question that kind of comes back, this goes back into our monitoring of evidence. How do we know these things about the Earth? Which seismic wave can't travel through all of Earth's layers, and why? If you know the answer to this question here, now, then you will know it when it's on the quiz at the end of the week. So take a look at that. Write the answer down. You could just write that or kind of make a mental note of it. But that's pretty much it.